invariant properties when you deform the surface. And if you have a family of these surfaces that you get by deforming what you started with, such surfaces as a family are called homeomorphic, like same shape. Right? So the technical definition of, there are lots of topology is the study of invariant, ANTS, the noun, the invariance of homeomorphic surfaces. Homeomorphic, technical word is damn. That's what I'm saying, feel my age. My short-term recall goes manifolds. Yeah, manifold. And what's a manifold? Oh, forget it. Study topology. Right. And the third one is differential geometry. So now this is undergrad level. Hold on. It's definitely senior level, and possibly senior M1. Okay. So senior level, first year master's level, sort of a mix of the two. The earlier chapters, senior level, and the later chapters more into M1 level. And it's differential geometry in 3 dimensions, ordinary 3-dimensional space. And the concepts and the techniques that you'll learn from differential geometry carry over into higher dimensional space. Now remember, one of the things that I plan to teach a couple of years from now, obviously, is string theory. One of the great hopes for a unified theory of physics that explains effectively everything that we know about at the moment. Like the big dream is that string theory will explain the existence of the 4 main forces in nature. From weakest to strongest of the 4, the weakest is gravitational force, 10 to power 40 times weaker than the strongest. Next is the weak force, as it's called, which is short for weak nuclear force, because it operates at the scale of the nucleus, very, very tiny range of the force. The next is the electromagnetic force that acts over an infinite range. And the strongest of all is the so-called strong force, which again is short for strong nuclear force. And the strong force also acts over a very tiny range, about the size of the nucleus, or less. Okay? And the strong force keeps the quarks together, and hence the nucleons together, and hence the nucleus together, instead of just flying apart, because nucleus consists of lots of protons, and the protons repel each other, remember? So you need a countervailing force to counter the repulsive force of the protons. The electrostatic, that repulsion is an example of the electromagnetic force, the second strongest. So string theory would account for all that. It would account for all the masses and the natures of all the various particles in the so-called standard model. Getting into particle physics a bit now. Standard model, what's that? Well, it boils down to the sum of 2 subjects, like it's 2 subjects combined. The electroweak theory, that's the merging of the electromagnetic force and the weak force. They've been merged, they've been unified. So there's a mathematics that is in common for the 2. They're just 2 cases of the same thing. And then there's something called hold on. So there's the electroweak, and the other partner in this duo, that is the standard model, is QCD, quantum chromodynamics, and that's the quantum mechanics of the strong force. In other words, the force holding the quarks together. There are 3 quarks in a proton, 3 quarks in a neutron, and the medium, if you like, the means that generate this force between the quarks, so-called gluons. In a sense, they sort of glue the quarks together. And the quantum mechanics of all that is called QCD, quantum chromodynamics. Chromo got something to do with color. The gluons and the quarks are both colored, and I don't mean in the sense of ordinary colors that we're familiar with, that we see with our eyes. Color is just a label, and it's sort of like a charge. So quarks have an ordinary electric charge, the usual positive and negative. They have those kinds of charges, but they have 3 other kinds of charge called red, green and blue. I mean, you call them alpha, beta, gamma. They're just labels, right? Just to distinguish 3 different kinds of quark charge. Anyway, there's a whole very elaborate mathematics and a lot of research still going on at the moment on QCD. It's a personal interest of mine, fascinated by it, because I have this big dream that there one day may be a femto technology, a femtotech, and the mathematics of that technology, the theory of it, would involve QCD. Right? So I intend to become as expert as I can in that field. And the standard model is about those 2 subjects, electroweak and QCD. Now, there have been attempts to bring, let's see, so to merge the 3 forces. So we've got electroweak, that's been well merged. If people have attempted to merge with that the strong force, so the QCD, so the standard model is still essentially these 2 parts. They haven't been merged fully yet. There have been attempts with more or less success or unsuccess. So if the standard model could be fully merged, then you'd have something called a successful GUT, G-U-T, Grand Unified Theory, which is a bit of a misnomer because gravity is still missing. And that's where string theory comes in. String theory hopes to merge everything, all 4 of them. So you'd have an explanation of what the natures of these 4 forces are, what the natures of all the particles in the standard model are, the gluons, the quarks, the leptons, the light particles like the electron, and so on. So all the particles in the standard model, and their masses. That's where the Higgs boson comes in. That's part of the standard model. The last part to be confirmed experimentally very recently, just a month or 2 back. Major discovery in physics, and physicists are all very, very, very happy about it. So it's confirmation of the standard model, the best model physics has come up with. But it's not complete, right? We need to go, and the standard phrase is go beyond the standard model. Anyway, string theory. I need to pop the stack, as the the computer people say. Yeah, why am I talking about string theory? Well, the strings in string theory, the little one-dimensional objects, extremely small, 10 to the minus 35 of a meter, the so-called Planck length, extremely small. And when they move through space-time, thinking in terms of relativity here, they don't trace out a line. Like if you move to a point, if you trace out the locus, that's the moving path. Like if you have a sparkler like you light a sparkler and it's at night and you just wave it around, your eye will see the trace of the burning edge of the sparkler. Well, that's what the locus is, you know, the trace over time. So if you move a point in space-time, you've got a line, and it's called a world line. Okay, but if you have a little string, a little length, and let's say you loop it, so you have a loop, the two ends connect, and then you move the loop through space-time, you'll get a sort of tube, a deformed tube. Right? And that deformed tube is called a world tube. Okay? So instead of modelling interaction of elementary particles by interaction of 2 points, you model it by the interaction of 2 tubes. And so you don't get point-like interactions, so you don't get the infinities that plagued quantum field theory when the paradigm model was point particles. Now you've got, in string theory, you've got world tubes, okay, world surfaces. And to understand how they interact with tubes merging and splitting and all this kind of stuff, you need topology. You need a lot of topology. You need to be a topologist. So string theorists have to have a pretty solid dose of topological knowledge. And that's where topology and differential geometry come in. Okay? So this is the undergrad senior M1 level, the beginning of your knowledge of differential geometry that you will take with you to higher and higher levels, to the highest levels, PhD 2 level courses in string theory, in topology and differential geometry. So these two then are essential. Okay? Background knowledge, preparatory knowledge for graduate level topology and differential geometry. And in M1 level we will do algebraic topology, which weds algebra, abstract algebra, and we'll do abstract algebra courses in graduate level M1. So we'll do abstract algebra, which